All right. Hi, everyone. So, yeah, the purpose of this video is to go over regression modeling and how we might apply it in our research, and basically just go over some of the fundamentals. Um, so, the plan for today is is to so we're going to talk about how to use regression to analyze relationships between variables. Um, We're going to talk about some fundamental concepts that are really important for uh, just getting a better understanding of what we're doing when we're using regression. And they'll start to give you a better idea of just what exactly the models look like and just give you some context for what the information is that these models provide us. And we'll go over an example with some real data. So we have talked in this class already about research designs where we use observational data. And essentially what we're doing is we're collecting data from people. We're taking measures on people, either at a single time point or at multiple time points. And in this context, obviously, we're just observing. We're not doing any intervention like we kind of talked about last week with the ANOVA framework. But it's also important to realize and to just understand that we can also apply regression modeling even when we have an experimental data. But a lot of the times when we have some observational data, regression models are kind of the way that we try to they're quite flexible in trying to add in multiple predictors and try to understand some of the functional relationships, the relationships between multiple predictors and some outcome variable. So a large portion of research does focus on using variables to predict some outcome of interest. So a lot of research that is done in the health sciences and kinesiology isn't always experimental. We're not always able to manipulate our variables of interest, or may not be feasible. So some examples are we might examine how variables in a theory predict an outcome of interest. So we might have some sort of theoretical model that explains how variables are supposed to be related to one another. For example, the theory of planned behavior is a basic theory of why people engage in particular behaviors. And we might take those variables that the authors of theory of planned behavior are supposed to predict or promote behavior, and we might measure them and then see, do they explain variation in an outcome of interest, something like physical activity behavior, smoking, diet, whatever it might be. We might examine how fitness tests or different skills tests predict sport performance. So we might have some measure that assesses how good an athlete is at some sort of important variable of interest, like how powerful they are or how strong they are. And we might be interested in seeing, does performance on this actual measure or on this measure actually predict some sort of sport performance outcome? And if we know that, that might be useful because then we might be able to, design some sort of intervention to target those predictors or try to promote those things in an athlete. And then a lot of research in epidemiology examines how different health factors and different health behaviors predict disease outcomes. There's tons of research on the relationship between smoking and all-cause mortality, physical activity and all-cause mortality, and obviously a little bit more challenging to assess, but also people's diets and the types of foods they consume and how that predicts disease outcomes. So a lot of the research that falls under this kind of umbrella of observational designs, applies regression modeling. And it's just important to realize that when you see a design that assesses variables at multiple time points or at a single time point, they're likely using regression. There's some form of regression, and there might be some different terminology and the types of things that there's in the way that they explain what the model is or what the framework or what the analysis framework is, but a lot of that too can be just jargon. So, but yeah, I mean, regression modeling is going to apply a lot to these types of research questions that we might have. And if you understand the fundamentals of regression, you can apply those fundamentals to lots of other statistical techniques. So getting a really good understanding of regression is something that unless you're only doing experimental work and you're only doing ANOVAs, regression is a very useful tool to get a really good understanding of the fundamentals and the assumptions and how to validate a model. And we'll talk a little bit about model validation. But if you understand that, kind of more advanced techniques can kind of build on from there. So in this context, we might have some outcome of interest, and we're going to assume that it's continuous or that it reflects some sort of continuous structure. So basically, people can take on a whole range of values in between some sort of minimum and maximum value. And that's it's kind of tricky because sometimes it's hard to determine how much a variable is continuous or not. Obviously some reflect a much more continuous structure than others, but when we start getting it obviously into binary outcomes, so like disease or no disease, obviously we need to move to a different type of framework, like a logistic regression framework. If we have count data, so like how many times someone exercised in a week, so like 0, 1, 2, 3, or the number of times, or maybe the number of health conditions that they have, then we might have to move to a different framework as well, something like a Poisson regression. But for the sake of this, we're going to assume that our outcome reflects enough of a continuous structure to apply it and with regression. And it's important because if our variables don't reflect a continuous structure, then it's going to be harder for us to meet our model assumptions around how the errors in our model, if our errors are actually appropriate and they're reflecting the structure they're supposed to reflect. So our outcome could be exercise behavior, so how many minutes somebody exercises a week or on average daily. Could be a scale assessing well-being and mental health. We could be looking at some sort of sport performance measure, so like how fast somebody is able to perform some sort of task. Could be job satisfaction or fulfillment. Could be how well the blood is flowing in the brain. So there's a whole bunch of outcomes we could assess as long as they reflect some sort of continuous structure. And again, another way to think about it, although it's not the best way to think about how variables, classifying variables, but the interval and ratio scale. So like interval being like a non-true zero, ratio being, any, can take on kind of like any value with a true zero. So like something like height or weight. But again, I mean, those aren't always the best way to classify data, but if you kind of go back to your first year stats courses, interval ratio data are kind of at least one way to think about it, as opposed to nominal or like categorical or ordinal, like ordered data. So our goal in this context is to explain or predict an outcome with a set of predictors. So, or we could have one predictor, we could have multiple predictors, but our goal here is to try to yeah, essentially predict an outcome of interest, to try to explain it with the condition of some independent variable of interest. Kind of the same, it's kind of the same idea. When we have an experimental design, we have some sort of manipulation, like participants get one treatment or the other, and we look at the relationship between that variable and some outcome. Same idea here. It's like kind of the idea where, like, if people have some exposure, let's say like how much exercise they do, or maybe how motivated they are for exercise, that's technically an exposure, but obviously we're not manipulating it, we're observing it, or examining the relationship with some outcome. So with motivation, it might be the outcome being exercise behavior. So that's kind of one way to think about it. And our set of predictors, they may be based on theory, professional knowledge that we have about our discipline. So we might have a good idea of what things should predict some outcome of interest based on past work and research. We might be doing measurement or validity work, so we might want to see, is this measure that we think that's useful, that might give us good information about what an athlete is able to do. Maybe we try to see how well it correlates with some sort of criterion, so like sport performance. Or we might have some exploratory research questions where we're trying to understand, maybe how variables covary together. And maybe it's not really developed by theory, but maybe we have data and we're just kind of curious. We want to see what those relationships look like, and we have maybe some ideas, but it's really exploratory. It's early stage exploratory work that may be guiding future more confirmatory work. So our predictors could be continuous. So they could take on a range of values between the minimum and maximum, and they can also be categorical as well. So they could be zero or one. Like for example, smoking status, 0 being no, 1 being yes. So we can use both types of variables. We'll stick to continuous and categorical, or pure categorical, like binary. But of course, we could have multiple categories, but we would have to do something that's called dummy variable coding, where we're making multiple categories for some sort of categorical variable. But that's a little bit beyond our discussion today, but there's lots of resources on how you might go about doing that if you want to stick with a regression framework. And that might be useful if you have a categorical variable that has multiple categories, and then you want to see its relationship with some outcome, but you also want to control for some continuous variable or multiple continuous variables. And regression modeling might work better in that case than in an ANOVA framework. So the research design that we're going to apply here is, we're interested in explaining or predicting some outcome based on some single predictor or multiple predictors. So first, we have to select measures that are appropriate for what you want to assess. So obviously, we all use different types of measures. Some things that we've talked about in class, like you might use a self-report scale. So participants, they fill out or they rate themselves on some sort of scale. We might be using some performance measure. So, how much force an athlete is able to produce in a certain test. We might use tracking measures where people obviously knowingly, they wear an accelerometer or pedometer that measures, for example, how much they're moving on a day-to-day basis or how many steps they're taking. So as long as we pick measures that are appropriate, that should work well for our purposes. And then we select a time frame of assessment. So we might do cross-sectional, where we're assessing all our variables at once. We might use a prospective or longitudinal design, where maybe for a prospective observational design, maybe we're taking a measurement at one point, and then another, 2 weeks or 3 weeks, where we want to create some time separation between our measurements, or more longitudinal. Maybe it's like a year later, we're taking some sort of measure on academic abilities and seeing if it predicts GPA or something like that in the future. So more longitudinal, or we might even have repeated measures data. And when we have repeated measures, we can take this regression framework and we can build it up, and we can incorporate predictors in the model in a similar way, but the model just gets a tad more complex because we have generally more things that we're interested in explaining. But anyways, yeah, we can apply these regression models to all types of data sets. And then we obviously need to select a sample who's going to complete our measures. So we might have them complete a survey online. We might ask them to, we might recruit people and send them a survey on SurveyMonkey online. They fill it out. They might come into the lab and do it. We might have them come into a lab and complete measures at a single time point or multiple time points. Or we might extract data from a repository. There's lots of data that's available, actually, for researchers that have been collected in, these big national studies or big cohort studies where people have been tracked. And so sometimes, if you can, and they're useful resources, if you're ever kind of interested in that type of thing, you can extract data that's been collected, and you can, analyze it for, a study, and that's done, all the time. So whenever you see these like big epidemiology studies where they're looking at physical activity and all-cause mortality, in that case, usually the data is not collected by the first authors, like the authors on the paper. They're taking the data from some repository. So just some context on that. Yeah, and then the participants are going to complete our measures. This point is a little bit redundant, but kind of just the idea that they're going to complete our assessments at different time points or all at the same time point. I'm sorry, I'm getting a little thrown off because the taskbar up top is covering my titles and my slides, so I can't keep having to wonder where I'm at here. But so our goal here is that we want to model our outcome of interest based on a set of predictors or explanatory variables. And we may have one predictor that we're interested in, and we may have multiple predictors. But basically, we have an outcome, and we think there's a set of variables that may explain why people are different in that outcome. So, for example, we might be interested in explaining why people exercise more than others. And we might have a set of predictors. We might have things like motivation, some factors like how much their parents exercise. We might have information on, obviously, demographics, like their age, gender, and so on. And so we think that there's some sort of relationship between these predictors and our outcome. Usually our variables, a lot of times, are selected based on theory. So there might be a bunch of different predictors that we're interested in, and we want to see, all of these variables explain unique variance in our outcome of interest. And sometimes we might use predictors or we might have multiple predictors if we're interested in controlling for certain variables. So like if we have some outcome and we have some sort of predictor that we think is related, well, we might know that there's some sort of variable that always kind of correlates with our outcome of interest. And so we might want to control for that variable and see, does our predictor of interest explain variation, above and beyond that covariate, because it might share variance with our predictor and the outcome of interest. So We want to see if holding that variable constant actually allows us, or our predictor of interest actually still explains significant variation in our outcome. So we might not be actually interested in the potential confounding variable, but we might include it because, because there might be some sort of, idea that like with this new predictor that we're adding into the model we want to make sure that it adds something additional to some sort of other predictor of interest. So, one of the ideas might be, one idea, not in the health sciences, but maybe in the achievement literature, for example, like life achievements or whatever, we might, one of the very strong predictor is intelligence of, for example, job performance. And so we think, and if that's something, if IQ or intelligence is a really good predictor of job performance, but then we have a new theory about like why people perform well on the job, we might want to, control for intelligence because we want to suggest that our theory actually contributes to something beyond the relationship between intelligence and our outcome of interest. So even though intelligence might not be in our theory of how job performance works, we might want to account for it. We may also have multiple predictors that we're interested in simultaneously, and we want to see, which of those variables explain, unique variation in our outcome, because maybe all of them are correlated bivariately from a bivariate standpoint, from just a simple correlation, but we want to know, does each one explain unique variance? And it's also important to know, just because some variable may not have unique variance with our outcome, it might interact with other variables. So it's important to keep it into our model and test for potential interactions. That's not something that we're going to talk about too much today, or we probably don't have time to get there. But it is something important to consider. Like, we might, just because some variable might not explain unique variance, we might keep it in the model and see, does it interact with the other predictors in the model? Just checking the time. So here's, where am I at here? Sorry. So our analysis plan, so we talked about that. Oh, that was the last point. So the regression framework works well for all these types of analyses, or all these types of data sets that we might have. And so our setup of a basic regression model is we observe a set of sample data. So we have people, they complete assessments on some sort of X variable. We consider X maybe our predictor, and we consider our Y our outcome variable. And so we see this, X1, Y1. So for each person, they have some sort of, or they have a score for their X variable, and they also have a score for their Y variable. And then we have a whole sample, maybe up to like 100 people or 50 people, 300 people. And each person has a score on those variables. And in this case, just a simple example, we might look at the relationship between how someone's mood or how grumpy they are on a scale of 0 to 100, and how much sleep they get. So those might be our X and Y variables. Our X variable is usually on the X-axis, which is sleep, is our predictor. Our Y, our outcome variable, is how grumpy or what our mood is. So negative mood, I guess. So this is just our basic setup of a regression model, where we have one predictor, and our so our model is our outcome is modeled. So our outcome is y, and the regression equation, or the basic regression equation, gives us an intercept, so that beta naught or beta 0. So that gives us an intercept, and in an intercept-only model, this would be the average of our outcome. So if we had no predictors to explain grumpiness, and the best way to perhaps describe the data would be to just describe the mean. That would be our expected value. And in this case, obviously, we want to add a predictor. But just so you know, when we have an intercept, it would be the mean without any predictors. And then once we add a predictor in the model, the intercept represents what the score on y is when all our predictors are equal to 0. And then we have this beta 1, and this is the estimated slope, or the strength of the relationship for the outcome, which is y, regressed on our predictor variable, which is x. And basically, and we'll talk about this more, but it's basically how strongly related the two variables are. And obviously, these interpretations slightly change with more predictors in our model, but for right now, it's just a way of, it's kind of like what we talked about in the effects, when we were talking about effect sizes for meta-analyses. We talked about the raw correlation. If we just had a single predictor model, that's essentially what we would have here. We would have a one predictor would essentially be the correlation between x and y. And in this case, obviously, it seems like there's a trend as people sleep more, their negative mood goes down. So their mood is better for the more sleep that they get. And then we also have an error term. So that E looking thing. I don't know what the Greek terminology is, but anyways, that's the error that's not explained by the predictor. And our errors are, and we'll talk about this more, but this is really important. Our errors are normally distributed with a mean of 0 and some sort of fixed or constant variation at each level of the predictor. And we'll talk about this more, but this is essentially, if our models are correct, they'll follow this type of error structure. This is pretty essential. If it doesn't follow this, then we know that we need to adjust something in our model. So our classic linear regression model, we have some sort of outcome y, we have our intercept, and we have our slope for our variable x and our error. And this is some notation, and it for representing the errors. So our errors reflect, or they should be, normally distributed. That's what that n stands for, with a mean 0 and a constant variance for every fixed value of the regression line. And so, and we'll talk about this more, but the fixed value of the regression line, that's that line of best fit, and all of the values around that line of best fit that you saw, those are the errors. But we'll talk more about that. So some basic terminology. So our y is our response, or our dependent variable. So that's the thing that we're trying to model. That's our outcome of interest. Our x is the predictor that we think is something that's going to explain variation in our y variable. And when I use the term predictor, I use it kind of loosely, just in the sense that it's just like an easy terminology thing. But obviously, if we're operating within a cross-sectional design, it's not like, it's not necessarily like prediction, like, seeing what's happening in the future, but it's kind of this idea that we're using, some sort of X variable, some sort of independent variable to explain variation in our outcome. And then we have our model intercept. As I mentioned, that's when, so as I mentioned, the intercept can be interpreted, you'll get a value. Let's say you're reading a paper, you do a regression model, you'll get a value for the intercept. That value represents what the value of y would be when all our predictors have a value of 0. And then we have our beta coefficient for our x variable. And this is estimating the relationship between x and y. So the strength of the relationship between x and y is assessed with that coefficient or the beta coefficient for our x variable. And these are unknown population parameter values that we're trying to estimate with our sample data. So if we're thinking from a frequentist statistic standpoint, we think of, there's some sort of population parameter that we're trying to estimate, that our sample, that when we sample, that's what we're trying to estimate with our sample. Our sample data gives us an estimate of that population parameter. So there might be some true population parameter for the relationship between how much exercise someone does and their all-cause mortality, for example. We're trying to, let's say we collect a bunch of data on a bunch of people. Well, we're trying to estimate that true population value. I think it's more of to be honest, I think it's more of a statistical concept. It works out nicely when statisticians apply that mathematically. And it's obviously like, it's not as like applicable when we think about it in our own research, but it's kind of the statistical idea that we're sampling from some population. And obviously these estimates that we get are going to have errors around them. And that's why we calculate p-values to assess, are these values, do they represent the null hypothesis, or do they represent some alternative hypothesis? And then we have our error, which is not explained by the predictors, and we have a variation for the error. So that's the variation around our best fitted line between x and y. So obviously for each value of x, there's a fitted value that's following this linear line, or it could be nonlinear as well. But in this case, it was, a linear line, and obviously not everybody falls on that line. Everyone who falls around it, they have error, and there's going to be variability. So we can assess the variability of that error around the line of best fit. So in this case, if we had data, we can think of our y variable, our outcome variable, as mood or grumpiness. Perhaps theoretically speaking, we could assess it on a scale of 0 to 100. But maybe in this case, it's not really realistic to get, that range of values. Maybe, more or less we have, something between 40 and 90 or 40 and 95. And that's also important to consider because the estimates that we get in our models are supposed to reflect the values that, that we actually have in our data set. So if your values only go from, 40 to 95, the inferences that we're making about our outcome of interest should, reflect that range of values, if that's all we have in our data. And then X is hours of sleep. So that might, technically range from, people may sleep, minimum 0 hours to 12 hours. In this case, in our data set, maybe we have people that only sleep, between 4.5 and 9 hours. And again, thinking about our range of data and where we can draw our conclusions from. And also you'll notice in your own data, there's going to be parts of your variables that, there's not a lot of responses for them, or people just don't score as frequently in those areas. So it's also important to consider, where the limits are in our statistical models in terms of, how far we can draw our inferences to. So like, if we have exercise as our outcome and most people exercise between 0 and 300 minutes a week, but then we had maybe just a handful of people at like 600, 650, 700, 900. Well, the values that we're using to, or the statistics that we're getting from our data don't actually really reflect those more fringe values. So when we're drawing conclusions about our data, maybe we wouldn't draw as many conclusions about those really, really active people, because where we have a lot of data, that's gonna play a role, or that's gonna influence our estimates a lot more than these more like fringe values. So when we're thinking about the intercept, this represents our estimated value when all our predictors are equal to 0. And usually we don't interpret the intercept value or draw much meaning from it, especially if it's out of range for our outcome variable. So maybe, our outcome, I don't know, let's say in this case, or in a different case, maybe like our intercept falls around like a score of like 0.5, but most of our, people in our sample range from, or actually what can happen is sometimes our intercept actually falls below our actual range on our outcome of interest, I'm quite sure. So, so that's why sometimes people will, center their variables, or like, let's say they have like a scale, particularly like if their predictor value only ranges between like 1 and 10, well, maybe you score it back where everyone's subtracted by 1, so that like our intercept would reflect, because if our intercept is a value that, so if we had an intercept so our intercept is when our x is 0, but let's say our x can't actually be 0, it can only be between 1 and 10, well then that doesn't really have a lot of meaning for our intercept. So maybe we might move our variables back a score on our predictor, and that'll potentially give us a little bit more meaning of our intercept. But, and I know I really just rambled on there, but just so you know, most basic part of this is that our intercept reflects our intercept reflects the value when all our predictors are equal to 0, and it's you can kind of think of it like if you had some predictor that was binary, so 0 or 1. This is kind of hard. I'm kind of going off on a bit of tangent beyond like what's here on the screen, but if you get the estimates right for your intercept and your predictor, let's say it's binary, let's say it's smoking is 0 and non-smoking is 1, well, our intercept is going to reflect our expected value on y when smoking is 0, and then if we're going to get an estimate for that predictor, and that's going to move up by how much that value is on x from that intercept value. Anyways, I'll stop trying to discuss that there. We'll talk about that more in a bit. So we have two coefficients that we're estimating. We have the slope of y regressed on x. That's our beta x value. So how much does y vary as a function of x? So basically trying to understand, what is the relationship between x and y? How strong is that relationship? And so we interpret our slope coefficients, if we're using this example, as my sleep increases by 1 unit, my grumpiness is estimated to decrease or increase if it's a positive relationship by x units. So basically we can see here, if you follow my mouse, as people's sleep goes from 7 to 8, we see this average trend down in terms of grumpiness. So their expected value, if their sleep is 7, so the expected mean value for people who got 7 hours of sleep is around 65, and the expected value for people who slept 8 hours is around 55. So our coefficient would be -10. So when we're interpreting raw regression coefficients, it's essentially, we'll get some sort of value for that beta coefficient. And if we were to increase by 1 unit on the predictor, like sleep, how many units are we expected to increase or decrease with a negative value on our outcome of interest? And so we get these values, these slope values, as well as our intercept value. So in this case, our intercept would be, 84 or whatever. That would be the positioning where sleep is, equal to 0. And obviously, in this case, it kind of runs off on the x-axis, so it might actually go a bit farther. But anyways, we get values for the intercept and the slope based on, or we derive the values that limit the amount of errors. So we can see in this case, we have, these, obviously this is a very strong relationship between these two variables. That's kind of just useful for a visual standpoint. But we can see how obviously there's this like downward trend, and we get some sort of estimated linear relationship between those two variables. And the idea is that we're trying to reduce the amount of error in the outcome of interest. So we have expected values based on the linear trend, and we get that value by trying to reduce the amount of error that we have, because we could draw all kinds of lines, obviously, right, to explain that relationship, and the one that's drawn or the one that wins in terms of, I guess, getting chosen is the one that reduces the error in the best way possible. So we could also have two predictors in our model. We could have x1 and x2, and we could have more, of course. So now our beta naught, our intercept, is the estimated value when both those variables are 0 simultaneously. So if someone in our sample had 0 on both variables, their expected value based on our regression estimates is the intercept, or their expected value based on those predictors is the intercept. And so our slope coefficients for our predictors are now based on holding the other predictor constant. And in this case, so now our beta 1 value would estimate the relationship between x1 and y. I shouldn't have put the y1 there, but anyways, the x1 and y, assuming individuals are the same on x2. So let's say you had a sample of people, and you want to know the relationship between x1 and y1. If you have multiple predictors, let's say you have one additional predictor, now it's the relationship between x and y assuming that that the two people are the same on X2. So let's say our X2 predictor is maybe gender. So now our relationship between X1 and Y1, for example, let's say motivation and exercise, our relationship between motivation and exercise here is based on the assumption that the two people are the same in their gender. So they're both male or both female or both non-binary or something like that. And it would be the same thing if the predictor was the other predictor was I don't know how much they've exercised in the past. So it might be like their motivation, predicting future exercise behavior, assuming that the two people have exercised in the estimated to be similar in their exercise behavior. So I don't know if I explained that exactly. I think I might have confused that explanation, but basically, if motivation is our predictor of exercise and we want to control for past exercise, so the relationship between motivation and exercise behavior now is assuming that the two people are constant or the same on their exercise behavior at baseline, because we might expect that, exercise at time 1 is going to predict exercise at time 2, so we might control for that in our model, and that's represented by our beta 2 variable. So here's an example of how we would look at, or how we can visualize multiple predictors in a model explaining variation in our Y outcome. So we have a Y outcome, and we have two predictors, X2 and X1. So the D part of our model, this would represent the unique variation that X1 and Y, share, or the covariance between those two variables. Then we have E, that would represent the covariation or the unique covariance between X2 and Y. And then we would have G, and that G, that's the shared covariance between Y, X1, and X2. So how those, three variables covary together. Or basically, let's say, we think X1 and X2, those two variables are going to be correlated with Y. But we also know that X1 and X2 are also, related to one another. So it might be something like, I don't know, like if we're assessing how well somebody sleeps at night, maybe our X2 is exercise and our X1 is how, I guess like how well they eat throughout the day, or maybe let's say how many vegetables they eat throughout the day. So we know that, let's say that that's related to how well somebody sleeps, but we also know that exercise and how well somebody eats, those are going to be correlated together, and they're going to share, correlation, that shared correlation between exercise behavior and how well somebody eats. That shared correlation is also going to covary with Y. But we want to know what is the unique variance that X2, that exercise explains in Y, controlling for how much vegetables they eat. And the same thing for vegetables, predicting our Y outcome. So our D, this would represent the unique relationship between Y and X1 that's not accounted for by X2. And E would represent the unique relationship between Y and X2. And as you'll see, usually if two variables are if two predictors are correlated, we might see a raw correlation for those variables in our outcome, but we're also going to see, once we include both predictors in a model, the relationships are going to be smaller. So that's why, you might see a correlation of like 0.3 that's significant between X1 and Y. But now that you've added X2 in, well, maybe that correlation completely drops out because all that correlation between x1 and y is actually shared with x2. That covariance between x1 and x2, that relationship with those two variables is also related to y. So so now our predictor, drops out of the model. Or it doesn't drop out. I shouldn't say that. It's just no longer significant, but that doesn't mean we should necessarily just remove it. We might want to include it because it keeps the structure of our model appropriately helped up. Although other people might argue that you want to remove it for parsimony, but others would argue that you should keep it, especially if you want to look at potential interactions and so on. Okay, so when we have our line of best fit, we have we're going to get some sort of error in our model, and as we were talking about, we have this line of best fit, that relationship, that estimated relationship between x and y. But obviously, there's always going to be error. Like there's not going to, the line isn't going to go through all our sample data. It's not going to count for everybody. It's just I guess, technically a best guess. And so each person's observed score is going to, there might be some that's directly predicted by the line, but there's going to be lots that vary around that line. So if, in this example, we see that for this one individual, their error is represented by, or the error for that individual is represented by the difference between their observed score and their expected score. It's the same idea like when we had with the ANOVA framework, where we had the intervention and the control group. For the intervention and the control, the expected value for each person in that intervention and the control group is the mean of the group that they're in. So like for the intervention, the expected value for each person is the mean. And the same thing with the control group. And that's the same idea here. It's just that we're, operating with a continuous predictor. But at each level of X, as people move up on the scale, for each of those values, each person also has, or for each of those values, you can think of it as like technically like a category. So you move from 1 to 2 to 3 to 4 as you move up. Each category, it's not a category, it's continuous, but each, sliver of on that continuous scale has an expected value on Y, has a mean value, and all of those people for that value of X are all of them have the same expected value on Y. So if I have a bunch of us have a value of 7 on some continuous scale, we fit some predictor to it, we all have an expected value, same expected value on Y. But our Y variable, what we score on Y might vary. So if for some of us we might be above that line, for some of us we might be right on it, some of us might be below. So this is just to kind of reiterate our discussion about the random error. So for each fitted value, the errors must be normally distributed. So we think of this, let's say, performance on this diagram as performance is on our y-axis. I actually don't know what it is. It might be actually the relationship between distance and speed or something. Let's say just for a more applicable example, let's say on our y-axis we have a performance variable of sorry, I'm very tired right now. Our y outcome is performance, sport performance of some sort, like how fast someone swam, and that's our y. That's our y-axis. People vary on that. On our x-axis, we have some sort of measure, some predictor. Let's say how fast or how what their speed is, their estimated speed. And so we see this, as people, are able to do the test better, or they have an estimated speed score that's higher, their performance on our outcome of interest goes up, because we can see that this linear, maybe it's represented the best by a linear relationship. It could also be curved as well, but in this case, it's linear. And at each level of speed, so people obviously have different speed scores. In this case, let's say we're looking at here at a score of like 6 or 7 right here. So for each fitted value, so there might be a bunch of people in our sample that follow along that have a speed score of 6. And so our errors at each of the fitted values, in this case, our errors have to be normally distributed, because you see here for each fitted value, or for the expected value based on someone's speed score, there's going to be error around that. And those errors at each level, all levels across our variable of speed, are supposed to be normally distributed. It's supposed to follow some sort of normal distribution where most of the errors cluster around that expected value, and then we have less error as it, as it gets more extreme. And then it's also the errors are supposed to have a mean of 0. So obviously we can see for this expected value, or sorry, for this our x value of 7 here. The predicted value, for example, for performance might be like something like 3 or 4. And so the errors that vary around that predicted value, they're supposed to have a mean of 0. So they kind of cancel. Obviously the positives and negatives cancel out to a mean of 0. And the variation of the error is supposed to be the same at each fitted value. So whether we have our fitted value is here or here or here or here, the variation of the errors around those fitted values, are supposed to be the exact same. And so and what this means essentially is that how much variability, or the size of the variation, or the estimated size of variance, is supposed to be the same at each fitted value for our y outcome. So how do we get the values for beta naught and beta x? So we use calculus. Obviously, we have computers that do this for us now. That's not something that I'm going to be able to, go through with you at this time. But essentially, we have calculus algorithms that derive the values of beta naught and beta x, that make the magnitude of our observed errors as small as possible. And this is based on the least squares estimator. So there are lots of different estimators for getting our expected values. The least squares estimator is one of them. You could also use maximum likelihood, where we're trying to maximize some sort of likelihood function. And you'll see maximum likelihood used a lot in more complicated statistical models. But for basic regression modeling, we can use either the least squares method or the maximum likelihood method, and we'll get the same results. But when we're using more advanced statistical models, like we're starting to incorporate random effects, like a random intercept, for example, because in this case, right, everybody has a fixed intercept, but we might vary that intercept for some reason. Maybe because we suspect that we're missing something in our data that we're not accounting for. Could be because there's a grouping structure of the data, so it's better to represent each group with their own intercept. And in this case, if we're using an estimator like least squares, I don't even know if you use least squares. It's usually like maximum likelihood or restricted maximum likelihood, we are going to get different estimated results. They might not have huge substantive meaningful differences depending on our data, but depending on how complex our data is, we might have to be a little bit more prudent about the estimator that we choose. So that's where you see that language, like we use maximum likelihood estimation, for example, like that's where that comes from. So we can also do hypothesis testing, obviously. So far we've just talked about, deriving some sort of relationship between X and Y. But these are also statistical estimates based on a sample of data. And so we're interested in whether these estimates are significantly different from zero. So what's the probability that there is a zero relationship between X and Y? And we can test the hypothesis using a test statistic, so like a t-statistic, just like we got a t-statistic for the mean difference between two groups. And it kind of follows the same logic, because it's like the beta estimates that we're getting in the regression model, those represent like how much we're expected to move on Y based on some value of moving, between, a certain value on X. So if we move by one score on X, how much are we expected to move on Y? Same idea with a mean difference. We move from 0 category to 1 category, how much are we expected to differ? And then we divide that by the standard error. Same thing here with our beta estimate, how much we're expected to differ on our Y value based on a difference on an X score. Let's say it's standard value of 1. We can calculate a t-statistic, dividing that estimated difference or the estimated relationship. We divide that by the standard error. And so usually when people report their regression model results, or you get regression model results, you're going to get standard errors. And if you divide your beta coefficients by the standard error, it's going to give you the t-statistic, and it's also going to give you a p-value. And we determine whether our data represent the null hypothesis or the alternative. The p-value is really small. We conclude that our data is more in line with the alternative, and we reject the null. So our assumptions are that we've correctly specified our model. Obviously, we can never do that. No models are perfect, but we have to correctly specify them. We can largely misspecify them by missing a really important predictor, particularly if that predictor is interacting between our X and Y. So like, let's say the relationship between X and Y, there is a relationship between those two variables, but maybe it varies based on some other variable of interest, and it's a complete model misspecification. And so we might see that in our structure of our errors. So they might not be normally distributed. They might not the relationship between our predicted values, and that's another thing as well, our predicted values and our residuals. We should see no relationship between those two values. And so we might not have a constant error variance, and we might not have normally distributed errors. Another assumption is that all our observations are independent from one another. So as we're sampling, there's no potential covariance between errors, meaning like if we're sampling from different, for example, different sports teams, well, maybe the errors are correlated, or there's some sort of covariance structure that's going on because people are nested within the same team. Let's say it's like some predictor variable and some performance variable. Well, maybe that relationship between that predictor and that outcome is different for different sport groups. And so there's, each person is not a random person from a sample, but rather, there's these covariance structures going on between, clusters or groups of people. And so that might not be a problem. We could sample data and we might actually, if our model errors actually look good, we might not need to do anything about it. But if our errors look really bad and our model fit is quite poor, and we know that maybe we're not accounting for that clustering, then maybe we might want to consider including accounting for it. And like I said before, we might use random effects models where we account for that clustering by giving each group their own intercept, for example, and that might help fix things because we're missing something. We're missing some variable that's accounting for that clustering effect. I mean, obviously the clustering in itself is accounting for that misspecification, but there might be something about those clusters that's giving rise to this clustering effect. Maybe there's something different about one team than the next, and if we had a variable that we measured, it would actually get, and we accounted for in our model, it would get rid of that model misspecification, and we might not have to account for the grouping structure of the data. So, so now we're going to just quickly go through a simple example with some real data. So in this case, an area of interest for me, this is a very simplified example, but basically based on self-determination theory, which is a theory of human motivation and well-being. So based on this theory, people will be more intrinsically motivated, that being they're more inherently motivated to do the activities that they're doing. So for example, if you have an athlete and they're practicing, well, if they inherently enjoy practicing, if they find it just the activity in itself to be quite rewarding and motivating, and they're not really doing it actually for any reason other than just the enjoyment of the activity. Well, based on SDT, self-determination theory, if they're doing it for those reasons, they're going to experience a lot, better performance and better well-being. Same idea, or like if, in an exercise setting, if people enjoy, if they're doing it because they're inherently rewarded by the activity, they're going to feel a lot better, they're going to perform better. So anyways, based on this theory, human beings have needs for competence, autonomy, and relatedness. Competence being how effective they feel, autonomy feeling like they have a sense of choice over their actions, relatedness being, emotionally and socially connected and having a meaningful connection with others in their social environment. And based on this theory, if people satisfy these needs, they'll be more intrinsically motivated and less extrinsically motivated, where they're just doing activities just because they feel like they have to, or because they're trying to get some reward out of it. So if we're applying this to the context of exercise, we might see if people who satisfy these three needs, are they more intrinsically motivated for exercise? And we might have participants complete measures of autonomy, competence, and relatedness at a single time point. And then we might have participants complete a measure of intrinsic motivation 4 weeks later. And so we might want to predict, or we might want to see, if people are higher on their need satisfaction in the context of exercise, does that predict how intrinsically motivated they are 4 weeks later? So we might look at a data set that actually allows us to, or that represents this type of data. So in this data set, we have about 559 people who completed the outcome measure or completed the predictors at time 1, and then we have about 403 of those people completed the assessments at follow-up. And so in this case, so what am I looking for here? So in this case, people, they completed So as you'll recall, they completed measures of relatedness, competence, and autonomy at baseline. And there's a bunch of other variables that they might have uh, completed as well, obviously in this case. So for example, for this, for relatedness, there might be 6, separate items or 6 separate scale items that they completed. And then we take the average of those 6 items, and we do the same thing for competence, and then we do the same thing for autonomy. So where's autonomy? Autonomy is right here. And so we also wanted to measure, so like we said, we measured intrinsic motivation for exercise behavior, so how much they find exercise inherently rewarding and enjoyable. So we look all the way down here. So obviously these are all the participants that completed time 2 measures. We can see that these time 2 represent the variables that were measured at time 2. I think intrinsic motivation is all the way down here. So we have for each, we have 4 questions that we ask people about their intrinsic motivation, and then we take the average for that scale. So these scores represent that average. And I think the scale ranges between 0 and 4. So potentially our scores are between 0 and 4. So let me see. So what are some things that we might start doing? So we want to predict our intrinsic motivation, or our intrinsic motivation variable based on competence, relatedness, and autonomy. So one thing we might do is we might want to just graphically, because it was kind of useful, right, to look at that graph between our predictors and our outcome the same way we did in some of the slides. We had a simple bivariate relationship. And so we might want to do that here. We want to see, how do, what is the relationship between, what does it visually look like? That might just give us a useful idea. So we have, this is our outcome, and we might want to look at how it correlates or what it just visually looks like with our predictors of interest. So our first one is relatedness. So then we, okay. So we can see here, relatedness, it varies between 1 and 6, and intrinsic motivation varies from 0 and 4. And obviously this relationship is certainly not as clean as the one that we saw in the slides, because that was just a very simple example. But here, what we might want to do is we want to see, what does that line look like? Does it look like kind of like it's a linear relationship between those 2 variables? And so we don't want to impose maybe a linear line exactly. So we might just fit a lowest curve, which is basically just a curved line that kind of just follows the relationship between the 2 variables, kind of in the way that it's supposed to follow. You're not imposing like a linear structure. You're not imposing quadratic curvature or a mean, I guess in this case, but you're not imposing anything, just some sort of simple, some very like non-fitted value, I guess is the best way. So it just follows the relationship and the way it's supposed to naturally. And so here, let's see. So we see the relationship between relatedness and intrinsic motivation. This is kind of like the line that it kind of follows. There might be some curvature here, but pretty much looks, quite linear. Looks like there's a positive relationship. As people get higher in relatedness, their intrinsic motivation also gets a bit higher. And we can see, like we did before with that line of best fit, we can see that there's kind of like this expected value for each level of relatedness. Obviously, it's continuous, so people go from 3 to 4, 4 to 5, and values in between. So let's say we're thinking of the value 4. We have an expected value maybe of 3 for intrinsic motivation, and people obviously vary around that. And that's, it's important to realize, because yes, you can have a strong relationship between two variables, but when people say, something predicts some sort of outcome of interest, but even like this, I think this correlation is around 0.4 or something like that, or which is, relatively strong in this context. Obviously, like if someone has a score of 4 for relatedness, they could be around a 3 out of 4 on intrinsic motivation. They could also be all the way down here. Same thing with this person here. They have a score of 6 on relatedness, but their intrinsic motivation, according to them, is quite low, where most people are very high. You could have, for example, another person with really low relatedness and high intrinsic motivation. So we obviously have error in these relationships, and that's why when we're talking about relationships between variables, it's expected values, it's expected relationships, and it's just important to remember that. So that's why let's say you hear something in the media, something is correlated with some sort of outcome, and it's easy to think, oh, well, is that I have that predictor, or that might characterize me, but there's going to be a lot of error around that expected outcome of interest as well. So it's just important to remember. So we'll just quickly look at the other ones. So competence, for example. So this relationship obviously starts to look a lot stronger. Again, competence ranges from 1 to 6. If we fitted a lowest curve, looks pretty linear. Again, we have error around that, line of best fit. And then same idea with autonomy. So I think if we just look at autonomy really quick, and here, obviously, this relationship looks a lot less less strong than the other two. And so if we fit lowest curve, again, we have a relationship, but it looks a little bit less strong. So another thing we might look at is the raw correlations between our 3 predictors and our outcome of interest. So we might just want to say how correlated from a bivariate standpoint, not controlling for the other predictors. Each predictor itself is, correlated with intrinsic motivation. So we can look at the bivariate correlations. And here we see, obviously, correlations, they range from -1 to +1. Closer to 1 means or -1 means a stronger relationship between the two variables. In this case, what we see is that intrinsic motivation is positively correlated with all three predictors, which is what we would expect based on theory. Competence is the most strongly correlated with intrinsic motivation. It's 0.61. Relatedness is next at 0.4. And then we have 0.32 for autonomy. So all pretty strong correlations. Clearly from the diagram, we saw that competence was the most strongly correlated with intrinsic motivation. It's also important to note here that each of these variables as well, relatedness, competence, and autonomy, they share a correlation with each other. So relatedness is correlated with competence quite highly, 0.52, that's pretty strong. Relatedness is a lot lot less correlated with autonomy, so like 0.18, but still significant, pretty small. But then competence is also correlated with autonomy, so 0.39. So they're all correlated. One thing, and that's important to consider, right? Because while we know that relatedness is correlated with intrinsic motivation, and so is competence, so is autonomy. But if people who are higher on, relatedness are also higher on their competence and autonomy and so on, well, how much of that shared covariance is also maybe all of it contributing to their intrinsic motivation, or correlated, I should say, with their intrinsic motivation. So what we can do with the multiple regression models, and we can try to parse that out. So let's see. So what we can do is we can look at the relationships between all variables and in the outcome, like we were talking about. So we can enter our predictors into our model. So this is just one platform we can do it on, which is SPSS. Another thing that might be useful to keep in mind is, let's see if we can do it or not. I think this will give us the raw correlations between the predictor and the outcome, just so we can see how they change once we control for other variables. So overall, I mean, I'm not going to get into all the details. This is just kind of like a general way that we might look at our results. But R squared, we get an R squared value. Basically, it tells us what percentage all our variables explain in the model. So we're explaining roughly about 40% of the variation, or 39% of the variation in intrinsic motivation. That's pretty high. And with our output, what we're most interested in is interpreting the model coefficients. So again, we get that constant, that's our intercept, that's our estimated value, and relatedness, competence, and autonomy are all 0. So, but again, relatedness, competence, and autonomy, they only range between 1 and 6. So if we really cared about our interpretation of that intercept, we might shift our variables down so that they all represent 0. But anyways, we're not super concerned about that. So we look at our predictors. We get a coefficient for each one. So recall that this represents the strength of the relationship. Obviously, it's in the units of our outcome of interest. So it's these estimates that are based on that. So in terms of like interpreting the size of the relationship, you can't really necessarily do that, but you can do it from a raw standpoint anyways. But basically, I mean, because all these predictors are on the same scale, then we can kind of say, well, we know that like the relation, we can say which predictor, I guess, is the strongest. And we can also kind of do that with standardized beta coefficients, which we see over here. So we get a slope coefficient, or an estimated relationship between relatedness, competence, and autonomy, and our outcome, intrinsic motivation. Each of these values are based on controlling for the other predictors. So basically, if you recall, our interpretation is for 1 unit increase in our predictor, our outcome or intrinsic motivation is expected to increase by this value. So for a 1 unit increase in relatedness, intrinsic motivation is expected to increase by a value of roughly 0.1. It's 0.4 for competence and 0.07 for autonomy. And also because we're controlling for that, each of these or controlling for these other predictors, what we're saying is that when we're looking at the relationship between relatedness and intrinsic motivation, it's controlling or holding constant competence and autonomy. So it's the expected relationship between relatedness and intrinsic motivation for two individuals, or for individuals who are the same on their value of competence and the same on their value of autonomy. For each estimate, we also get a standard error. If we take our beta coefficient and we divide it by our standard error, that gives us our t-statistic. You recall, obviously, larger t-statistics represent a smaller p-value. So in this case, our relatedness variable, it's significantly correlated with our outcome. So less than 0.05 if we're using that cutoff. Our competence variable is our strongest predictor, and our t-value is quite large. So our t-value is based on, our standard error size and also the strength of the relationship. And another thing you'll notice is that autonomy, it's no longer significant at 0.05. It's close to 0.05, but it's no longer statistically significant. So what that kind of shows us is that once we're controlling for relatedness and competence, autonomy is not as strong of a predictor of intrinsic motivation. And that's kind of relevant to know, because you might say, well, what really is the most important? But this is just the start. So autonomy might also be, if we were to create an interaction with maybe the relationship between competence and intrinsic motivation is much stronger for people who also feel the need for their need for autonomy is satisfied. And so this is just a basic starting point, but it also tells us that competence, roughly speaking, is also the strongest predictor in the model, or explaining the most variation. But there's some other statistical tests that we can do further to confirm that we won't talk about here, but just based on the size of the relationship, we can kind of infer that. These standardized beta coefficients, that's the coefficient in standardized units. So if you were to, for example, with this competence one, if you were to increase competence by 1 standard deviation, you're expected to increase on intrinsic motivation by 0.5 standard deviations. That's kind of it's just moving from these raw units to standardized units. Same way, it's the exact same thing we do when we go from raw differences between two groups to a standardized difference, like a Cohen's d score. Just another thing to talk about. So like we talked about, just to kind of wrap this up, for each person, they get a fixed value or a predicted value, and then obviously they have a residual. So what we can do is we can start to kind of consider, what do our residuals look like? Do they look reasonable? But we can save our predicted values and our unstandardized residuals. And once we run that model, we look all the way at the end of the data set for each person. I don't know why it gives a predicted value for each person in the model, but it doesn't really matter, because these are clearly people that just weren't actually in the model at time 2 because they didn't complete the assessment. But anyways, each person gets a predicted value. So for this person 2, their predicted value on intrinsic motivation is 2.6, and clearly they were below that value. this person um, had a predicted value of 3, and obviously they were below that value, or sorry, they were above that value, so their residual is positive. And like we said, for each predicted value, as we go down, those predicted values, they range, between, they technically could range between the scores on intrinsic motivation, but we actually just look at them really quick. The predicted and the residuals, we just look at the so the predicted values, they range from 1.4 to 3.8 for intrinsic motivation. So the maximum is 4, obviously, but the maximum predicted value is 3.8. The minimum predicted value is 1.4. And the residuals, they range between -2 and 1.4. And so one way that we can actually start to assess the validity of our model is we can look at the relationship between our predicted values and the relationship between our residuals. And because, like you would have seen in that diagram here, for each predicted value, the residuals are supposed to be constant. So there should have a constant variance, and they should be normally distributed. So based on that, there should be no relationship between the predicted values and our residuals. So the correlation essentially between each of the predicted values and the residuals that we have for that predicted value, there should be no positive correlation. The correlation should basically be 0. If we start to see a relationship between our predicted values and our residuals, then that means we're starting to violate some of the assumptions of our regression model. So basically what we can do is we can look at a graph to see our fitted values versus our residual values. So our fitted values we'll put, or our predicted values we'll put on the x-axis. And for each fitted value, the residuals should be, not correlated. And here, so this would be our predicted values on the x-axis. Our residuals, they kind of, for each level of the predicted values, obviously, we see this variation. And the estimated variation is supposed to be constant with a mean 0. And there should be no, relationship between them. And so if we fit a lowest curve, then that looks pretty good. So basically, that tells us that there's no real relationship between our predicted values and our residuals. Obviously, at the end here, the end of the predicted values, that there's a bit of this like kind of weird, shape downwards. That tends to happen with more like realistic real world data, but it's not something that we would be overly concerned about. And so our model, in this case, it doesn't look too bad. It looks pretty decent. But if you were to start to see, some weird curvature where this lowest curve, went up and down, then we know that something's wrong with our model, that we need to change the variables, or we need to add a variable, or we might need to add an interaction or something. But that's pretty much it for this. If anyone has any questions on regression modeling and the things I talked about, I know I got a little rambly at times, and I, maybe the way I explain things kind of, was getting turned around, or maybe didn't come out as clear. If you have any questions about regression modeling, I'm always happy to chat. But yeah, thank you for listening, and see you next week.